Alright, let's move down then to number 8. We've got this set of numbers, and it looks like we first need to classify each one as being a natural number, an integer, a rational number, or a real number. That might be more than one of those. Well, 2 is certainly a natural number, and it's also an integer. Sorry, I don't know why I wrote that. I'll just put check marks. Yes, that is, 2 is a natural number. It's also an integer. We can express 2 as a fraction, like 2 over 1, so it is a rational number. And we know that all numbers are real. For that matter, let's just immediately check everything in the real box. Now, the square root of 3, if I put that into the calculator, I would get, let's work that out, square root of 3 tells us that I get 1.73 blah 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 blah. Well, that's clearly not a whole number, so it is neither a natural number nor an integer. Is it a rational number? Well, a rational number needs to have a decimal that either stops or repeats, and there's no really clear repeating section here. I know that you might think it repeats at the end when you see 0808, but that's not sufficient evidence to be sure that it will repeat after that. Turns out that the only square root numbers which are rational are perfect squares, but 3 is not a perfect square. It will not be a rational number. And negative 2 over 3, well, clearly it's not a whole number, nor is it an integer, but certainly it can be expressed as a fraction. And so there's your answer to part A. Part B, a function is given with this particular equation, and you've been told that x, the domain, only includes negative 2, positive 2, and positive 3. So we need to write a mapping diagram. Here's our domain with our values of x, negative 2, 2, and 3, and each of these is going to be mapping to something in the range. Let's work out what those range values are. So when we have an x value of negative 2, then we have 2 times negative 2 squared minus 3 times negative 2. And I'm going to skip a step here. You can check my work a little slower if you like, but it maps to a value of 14. Let's now check the next domain value of positive 2. It's 2 times positive 2 squared minus 3 times 2. And again, I'll do this in my head, but you end up getting a value of 2, and so 2 is mapping to 2. And lastly, f of 3, let's see what the corresponding range element is for the domain element of 3. 2 times 3 squared minus 3 times 3. That gives us a value of 9. And so 3 is mapping to 9. And then we're supposed to write down the range of function f. Well, we can see the range now. It's these 3 values, 2, 9, and 14. So the range of f will be 2, 9, and 14. Moving down then to number 9. Our function has been defined as f of x equals 1 plus x cubed. We're told that x is an integer, any integer between negative 3 and positive 3. Now we're supposed to list the elements of the domain of the function. Well, we can see the domain. They are the integers from negative 3 all the way up until positive 3. There's the domain. We're also supposed to write down the range of f of x. Well, that means I'm going to have to figure out what each of these domain elements maps to. That's going to be a little bit tedious, so I've got a clever way of doing this a lot quicker. Let's go into the calculator and type in this function. I'll just clear my old ones. And I've got the function 1 plus x cubed. Now, instead of pressing graph, I'm going to press second graph, which will access the table of values. And this shows us what the corresponding y values are for all of our x values. And if I scroll upwards in my table, I'll see that I've got now my x values from negative 3 to positive 3. Look, these are the corresponding y values. And so my range then will be from negative 26, negative 7, 0, 1, 2, 9, and 28. Right? So that's a clever way of using your calculator to save you a lot of time. Instead of working out each one individually, just enter the equation of the function into y equals, and then have a look at second graph so you can see a table of values for all of the domain elements that we're interested in. Number 10. So our function 3x minus 5 describes a mapping from our domain elements over to our range elements. We need to find the values of p and q. Alright, so we need to find out if 1 is mapping to a range element of p. 1 is an x value, isn't it? So let's type it in. It's our x value, and so we're going to have 3 times 1 minus 5, which gives us negative 2. So that means that 1 is mapping to negative 2, and we can conclude then that p is equal to negative 2. Q, however, is an x value. And so if I type in a q, we've got 3 times q minus 5, but we know what it equals. We end up getting a value of 7. So 3q minus 5 is equal to 7. Let's solve that equation. 3q minus 5, that is your function at q, is equal to an output of 7. That means that 3q equals, if I bring the negative 5 to the right, becoming a positive 5, we get 12, divide both sides by 3, and q is equal to 4. And the last question is to write down the domain and range of these two following functions. We know that to find domain and range, we can just smush them onto the x-axis and the y-axis respectively. It's one way of doing it. It looks like I've covered everything on the x-axis that is less than negative 3. I can't really tell from my resolution here, but this to me looks like it might be an open circle. If I'm right about that, then we need to say that our domain of this first one is going to be everything strictly less than 3. And I know that you might argue that we don't know if it keeps going or not here, but it certainly does extend to the very edge of the graph. Let's assume that it keeps going forever. And the range, we're now smushing everything onto the y-axis. And so we can see that we've covered everything from negative 2 up to positive 2. But if we're assuming that this line goes on forever, well then our range would be everything that is less than or equal to, because we did reach 2 itself, positive 2. And part B is a little easier because this is a discrete relation where we can simply read off all of our x values. Look, if we smush them down to the x-axis to see what x values have been represented, we'll see that we've simply got a domain of the set of values, negative 3, negative 2, negative 1, 0, 1, 2, and 3. Meanwhile, our range is going to be now all of the y values that we see represented. If I smush those over to the y-axis, I end up with only 4 values, 1, 2, 3, and 4. And because there's nothing in between, I've got to list them as independent elements within a set in that manner.